Let's talk about set builder notation. This is a way of describing sets in a very simple way using propositional functions. Remember that sets really have one thing about them. For any element x, I take it to be anything at all, anything in our universe, and any set A, I have this exact statement always true. X is in A, or, exclusively or, X is not in A. This is the idea that if I take any element, anything that could possibly be considered an element, and anything that could possibly say what I call a set, either X is an element of A or it's not an element of A. Not both, not neither. Exactly one of those two things happens. Which means that we can do things like saying X is in A if and only if some property holds. That is, we can use a definition of my set A by saying no matter what element I pick, X is an element of A if and only if some propositional function P of X is true. And this is essentially equivalent to using the following notation. So to define my set A, I can say it's equal to, using curly braces to denote the set, it's going to be the set of things X such that P of X is true. That's what we're saying. So on the left-hand side of the colon, which is also sometimes a vertical bar, the left-hand side is the actual elements as I would see them in A. And on the right is a condition on the variables of that left-hand side of what matters. So here's a few examples of ways of describing different sets. So first, let's consider the set E, and I can define it in terms of the set of elements n such that n is an even integer. Well, what we mean by n is an even integer, that's an exact replacement. I can say there exists an integer k such that n is equal to 2k. That's really what the definition of n being an even integer is. So these two things are definitely the same set. I'm talking about the same set of elements n with the same propositional statement I claim to be true. An odd integer would not fit in here because n being an odd integer would not satisfy this proposition or this proposition. However, look at this third way of describing the set. What I'm talking about is I'm saying, well, my proposition is just saying k is an integer. But on the left-hand side, I'm saying my element that I put into E is 2 times k. So even though my propositional function in terms of k is true, k is not actually the element. I'm saying 2k is the element. So here's another way of describing it. So this way does not exactly fit this definition. So what I'm going to do instead is I will rephrase this. So another way of using set builder notation is to say, well, the elements are some function of my elements, given that this propositional function is true. So in this definition of my even numbers, I'm saying, well, let k be any integer. And then I'm going to put in the element 2k. So my function here is take my k and multiply it by 2. Now consider my set S. I define it to be the set of integers n, such that n is a perfect square. But what I mean by n being a perfect square is that there exists an integer m such that n is equal to m squared. So going from this set builder notation to this is really just expanding what I mean by n being a perfect square. I'm saying there exists an integer m such that n equals m squared. But I can say, well, if there exists an integer m, why don't I just use m squared and just say, well, okay, let's consider the elements that are m squared, where m is an integer. And therefore, I'm really just saying the outputs of this function for m being an integer, that's what I'm talking about.